Hey, welcome back. And today we will continue where we left off talking about reactions of amines. Reactions of amines. So right here, let's see, share screen. We need to pull that. Okay. Reactions of amines. So start with Hofmann elimination. How do we spell that? Hoff, one F, two N's, Hofmann elimination. It's one where we're going to take an amine, and it's going to be our leaving group, and we're going to turn this into an alkene. First, you have to make the amine a good leaving group. Now, when we do this, Hofmann, it's going to be anti-Zaitchev's rule. Remember, the Zaitchev's rule is one where we try to make the most substituted alkene. So this is going to work opposite from that. That it's a loss via an E2 mechanism. So remember, E2 is leaving group leaves, and we form an alkene rather than an SN2. So we can break it down into 3 steps. Step 1 is going to be our exhaustive methylation. Step 2 is going to be convert to ammonium hydroxide salt. Salt. And then 3, we're going to heat to promote E2. So let's take a look at this. Let's take a look at this actually in action. Step 1, we start with some sort of primary, start with at least in this case, a primary alkane, primary amine, sorry. 2. So we have to exhaustively methylate this. Iodine. And we're going to keep adding methyl groups to the amine. And kind of, we talked about this. The amines will add with RX and keep it, that we can alkylate amines like an SN2. So we're going to form our substituted amine. So this is now plus CH3 I minus, and of course 2 equivalents of HI. So we've exhaustively methylated. We've learned about that reaction last week. Alkylation of amines, and one of the things we do is exhaustive methylation. Now, the next step is to turn this into a oxide, the hydroxide. So, in this case, from this starting point, CH2 and 3 minus, we're going to add a half equivalence of silver oxide and a half equivalence of water. If we have 2 silvers, we can do this, essentially we can do this oxidation twice. per amine. So what that's going to do is we're going to form a silver iodide salt. Silver iodide salt, and we're going to form hydroxide. So we're going to just essentially exchange the iodides with OHs. Form product CH2 and CH3 OH. That's minus and that's plus. All that's still the same. Essentially, we're just removing the iodine and replacing it with hydroxide. Last step. So this is now, and so that's crashed out as a solid. So this is now a good leaving group. So CH2 and CH3 OH. Now we're going to just heat that, say 150 degrees, just to try to dry that off. And what we're going to form is a monosubstituted alkene. So we're going to, in fact, let's see. Problem is, this needs to be, well, there should really be another CH here. We're just knocking the next one over. So we're essentially losing a hydrogen. It's going to hydrogen from the second group. Adding this in, because essentially we're pulling it out of the R group. We're essentially losing a hydrogen to form water. We're forming methylamine, trimethylamine, and water. So forming essentially very good leaving groups that essentially induces this beta elimination. As I said, there's ways you could probably, typically you wouldn't want to lose it from this end. If I lost it from our group that wasn't a methyl, say ethyl, we could put a disubstituted alkene. But this is specifically going to be a monosubstituted alkene. Or say this wasn't a CH2, but was disubstituted alkyl group. Well, we can have a disubstituted alkene. But there has to be a hydrogen on that secondary CH2. So we're going to form the least substituted Hofmann product. And so, in fact, oftentimes when we look at certain reactions, the Zaitsev product is the most substituted, and we call the least substituted the Hofmann product. So, but this is because of this, the attack has to be anti-coplanar to the bulky trimethyl ammonium group. That because it's an E2. Because it's an E2. Let's just draw this. So, draw on here. Here's our this hydrogen that's being lost is anti-coplanar. Same plane as this. So that remember, as this gets lost, we pull away, the lone pair is essentially swinging up to attack and form that, and that causes this to swing up. This is bulky, so this hydrogen has to be opposite of here. So this is what forms this. is attacked by hydroxide. That makes this work. So, for example, like if, hypothetically, this doesn't have to be primary. It doesn't have to be a primary alkyl group. Probably works better with primary, but like, let's look at a substituted one. So let's say we have this. So now the Zaitsev product would clearly be, the Z product would clearly be, sorry, this guy. The Hofmann product is going to end up being this guy. We're going to form preferentially the Hofmann product because of that. So essentially we're saying like we have to be anti-coplanar. So this one has essentially the, let's see, I'm trying to look at my little notes real quick. Okay, yeah, the reason, so if we look at this guy from the, what is that called? This configuration, when we look at this, so look at it from here, and I'll just NR3. And here's our ethyl and a hydrogen. We need anti-coplanar. OH is going to attack here. Opposite of this guy. There's no steric interactions with any of these guys down the line. Now, so this is results in the Hofmann. We look at the Zaitsev product the other way around. We have we'll put N methyl methyl. Okay, looking at this is be the one we attack to kick out the N. But what we have here is a steric interaction between this methyl group and that bulky nitrogen. The steric interaction makes this an unstable mode of attack, that we have to leave that methyl close to something essentially staggered, but still staggered adjacent to that nitrogen in order to that bulky nitrogen to kick this off. And so because of that, the attacking of that hydrogen is less stable. And even though Zaitsev is often a more stable, more energy stable product, obviously this is a more high energy intermediate. And so a high energy intermediate means, well, it's not likely to form. Maybe it would be the kinetic product. I mean, this high energy intermediate would be the thermodynamic product, but it's not the kinetic product. So we don't see that as much. We see the Hofmann. So just a quick example, some examples of this guy. We could do like, oh, hey, here is pyridine. No, this is just So cyclohexamine. So step 1, I use excess iodide. Step 2, silver iodide and water. And then step 3, I use heat. And what we're going to form, this one, they're identical, so we don't have to worry about it. So this one, we just form a amine. But now, here it gets a little bit crazier. What about with nitrogen into the ring? So this guy, same steps. Same steps, step 1, step 2. But we have something a little bit different. Step 1, the methyl iodide. Step 2, silver nitrate. Silver oxide and water. And something a little bit different. So let me erase that. Try to make this look at least semi-drawn competently. So we have the ammonium hydroxide. Now, because of the nature, because of the ring-like structure, this is a leaving group. And yes, it will leave in the presence of heat, but not going to leave necessarily as we think. We're going to form the least substituted amine. This is going to leave anti-coplanar. So we're going to kick this off and form a. So looking at this, we're going to either form a double bond between here. I'm going to actually mark this double bond either here and kick off that, or a double bond here, or a double bond here. And so right here, problem with this region is because of the ring structure, it's harder to get anti-coplanar. It's harder to essentially adopt our structure. But this guy, we have free rotation. So this one's going to be our preferential double bonding spot. So as this leaves, we're going to see this going that way to form that double bond. That goes, actually we're saying the electrons from that hydrogen going to form that way. As the electrons from that hydrogen going to go that way. And see the electrons going this way. So we're going to form an amine at the end of that ring. And it's going to ring open. So is it 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Then so we ring open that. Now, so that, I mean, that's just some of the crazy stuff you can do depending on how the rings, how your nitrogens are set up and being used in there. One more example. We have step 1 and 2. 1 and 2. We have our methyl iodides. We have our silver oxide. You're going to have, whoa. Okay, so looking at from here, what's going to happen? Well, you could see loss both ways. So you're going to see actually a mixture of products. We could see lose in one way versus lose in another, because free rotation here means this could be our, hypothetically, we could cleave this bond and become a leaving group, or I could cleave this bond and become a leaving group. Both ones would be equally stable. So we could form this, and of course, that would be our side product. Or we could do that and form our ethyl dimethylamine. So both of those would be products, and those would be equally likely, because both of them, we would see free rotation around the methyl group at the end, and easily enough to form the anti-coplanar arrangement from the E2. So Hofmann elimination, it's a kind of complicated one. It uses, but if you can recognize it, you can flashcard it. It uses 3 steps: methyl iodide, silver, oxidized silver. That's going to be a reductant, and then we're going to have our heat. So we have oxidation of amines. The amines are usually pretty easy to oxidize. This one's called the cope elimination. So we can essentially, if we look at these guys from least oxidized to most oxidized, we have our your basic amine. We have our imine, so our double bond to nitrogen. We can have our ammonium. We can have our hydroxamine. We can have, and we're still starting to get more oxidized now. We can have our like ammonium hydroxide kind of situation. Still single bond, so you see the charged is greater than the neutral. There's a charge greater than neutral. Now we can have start our first nitro group. And then our final situation is our full-on nitro group. Full-on nitro group. So we could go from all the way to here, all the way to there. That'd be the greatest degree of oxidation. Now we can undergo these oxidations through many different methods. The most common one is peroxide. But we could also use permanganate. That's another common oxidant. We've seen these guys before. And of course, some sort of peroxy acid is another guy. Don't forget this guy. Don't think, oh, this is going to do some crazy stuff. Like, The big part is the peroxide part. So like say, if I say this is chlorobenzoperoxide, the chlorine isn't playing a part, the benzene isn't playing a part. The chlorine and benzene is just to stabilize this guy, withdraw electron density. So the big part is this double oxygen, this peroxy. That's where it's coming from. So all these guys will act as oxidants. I'm just going to put a generic O is going to be a O. This is an oxidation. But with that in mind, I just want you to know this could be a hydrogen peroxide or it could be a proxy acid. It could be permanganate. All these guys would work. All these guys would work. So we can go from a primary amine. We oxidize. You do it. And a hydroxyamine. We oxidize it again. Get a nitroso. And if I oxidize it again, I'm going to get the nitro. Now, these guys will have complex reactivities. So you're going to actually get a mixture. You're not going to get just all of one or all of the other, especially if you have, unless you have a large excess of our oxygen. If I do say, so that's what the primary, the secondary amine, you're limited on what you can do. So with a secondary, I can only really oxidize it once. You're going to get, hydroxylamine. But you're going to get some side products as well. So, and of course, a tertiary amine. All tertiary amine can still go one step further, similar to that. So R3N. If I oxidize that, usually either with peroxide or with our peroxy acids. So permanganate, not so much. We can form that amine oxide. Once again, that's also very limited on what you can form. So now the positive charges on nitrogen will lead to what's called the coelimination. That the oxide on these oxidizing will act as its own base and do its own attack. So like, for example, the idea here is that if we oxidize this, so we have, say, RCCN R prime. If I've oxidized this, to get to this point, to the amine oxide, we're going to go from the amine oxide. This guy is going to act as its own base, deprotonate that, and pick that up to make that a good leaving group. So we're going to kick off form a hydroxyamine. So we're going to form essentially, oh, hey, byproduct is R, the di-substituted alkene. In presence of heat, it's just a different version of the Hofmann elimination. It's saying, oh, okay. Instead of having a separate hydroxide that's going to use the base, we're going to do this with a oxidized internal amine. So to form an amine oxide, that will kick itself off. Now this is a one-step concerted internal elimination, but it's also still going to form a Hofmann product. One advantage is it's going to have much milder conditions. So now you notice, so the Hofmann kind of favored external alkenes. This one would get an internal alkene from this tertiary amine. So it's just another way to form an alkene from our starting amine. Now we can also have some reactions of amines with nitrous acid. So we're going to have reactions with NaHNO2, to what nitrous acid is. Now, nitrous acid is not very stable, so it's going to be generated in situ by mixing sodium nitrite with HCl, cold and dilute. So we're going to make HNO2. It's not going to want to hang around for too long. So in HNO2, we have this in acid. HNO2 does this. HNO2 plus protons is going to generate HOH and we have a lone pair. Plus okay, so reactions of amines with HNO2. So HNO2 will be formed in situ with cold dilute HCl mixed with NaNO2. But why do we want HNO2? In acid, we essentially form a good leaving group, water, and we form a nitrosium ion, which is going to be our reactive intermediate that's going to attack our amine. We have this, and it could go between that and our double bond, much like carbonyl, just like CO. So we have our, essentially, HNO2 in the presence of acid is going to generate nitrosium ion. So this nitrosium will form what's called a diazonium. So what we're going to do with a primary amine with HNO2 and acid, we form with this R triple R with an N, triple bond with an N, and water. So what this is called a diazonium. This diazonium is going to be a really, really good leaving group. The idea that essentially this will kick this off and form a carbocation useful for various other reactions. Okay, so let's look at the mechanism here. The mechanism here is that we'll go back. So starting from our primary amine and our nitrosium cation. We have our primary amine, our nitrosium. Minus 2. Once again, standard Lewis acid, Lewis base. Nitrogen is carbocation. It's maybe not as stable as it wants to be. It's 2 electrons short of where it needs to be. The amine, standard Lewis base, has that lone pair that can be used to attack. So as that attacks, we form the di-nitrogen bond, a 2 nitrogen bond. So this becomes positive now. Separating these charges. Too many electrons on that oxygen. Now from there, in the presence of water, because water's a byproduct when we form the nitrosium, the water is going to pronate the the water is going to act as a base and depronate the amine. There. So from there, and we're going to just repeat this. NH, N, O minus. That's a negative charge. So we're going to repeat it. So we got that. So that's a sorry, that shouldn't have been charged. My God, what am I doing? What am I doing? Okay. From there. Now, since we formed water, we formed an acid as a byproduct. That acid can now pronated by this. And this is going to swing over here. So we formed this compound. We have NH plus, double bond N, OH. And of course, this can resonate back and forth given the positive charge on the oxygen or the positive charge on the nitrogen. And we're going to just repeat that again. Water is going to depronate. To make acid. And then acid is going to pronate to form a good leaving group. Oh, hey, there. And that way we form the diazonium. Once we've kicked off the water, it's not really going to come back. So we form the diazonium. This diazonium, not super stable, but it provides a very, very good leaving group. The idea is that, hey, this is very reactive. We form this, we turn an amine to a diazonium, so a way to kick the amine off and form a electrophile. Now, with that in mind, this diazonium is now a really good leaving group, useful for all sorts of SN reactions, all sorts of beta elimination reactions, ready for all sorts of rearrangements. Because the idea being that Rn, N, this will very easily form R plus and 2 gas. If this floats away, we're left with, it's not going to reverse its way back. So this is going to be a very good intermediate. If you say, how are we going to remove an amine? How are we going to remove an amine and replace it with something less reactive? How are we going to kick off amine, replace it with a chloride? How are we going to kick off amine, replace it with I don't know, how are we going to kick off amine and form a double bond Zaitsev style, and not Hofmann arrangement. You form the diazonium, kick that off, and you can do a beta elimination with a bulky base. Now, that typically only works with primary amines. If I tried to do this with a secondary amine, I only have, I only have one H. So if I do the attack with the nitrosium, I can form, oh, here's my N. So, jumping ahead of myself. Here's my N. Here's my O. Here's my R. H. If I add then water, 2 steps, I'm going to have R and NOH. I can't go past this N-nitrosoamine. I cannot get past here. We cannot get to the nitrosium, the diazonium, because we don't have any more hydrogens to remove. So this diazonation will only work with primary amines, and it will not even start at all with, I mean, you can't get past this step if it's a tertiary amine. But so, why are these useful? Well, let's look through a series of reactions that use these diazonium salts. Just to give you a wide scale idea of where we can use these. That especially arene, so phenyl diazoniums are stable in water from 0 to 10 degrees, but they start to decompose above 10 degrees Celsius. So you could, and if you ever let them get dry, they will explode. But for these guys, you can replace the diazonium. So we're going to give some examples of, we can replace the diazonium with hydrogen, so just a phenyl, or with an hydroxyl, or cyano, or with some sort of halogen. All these are just examples of things we can do. So we're going to give some more examples in just a minute. So example of what you might have to do to prepare this. So let's start with toluene. Toluene is a methylbenzene. Well, if I add nitric acid in the presence of sulfuric acid, this is a nitration. concentration. NO2. I'm going to add this probably para to the methyl group in the presence of, like, say, our reductant ion with HCl, and then we use base to neutralize this, form, so we don't have we don't want ammonium, we want the basic form. We can form amine. Then in the presence of Na, NO2, HCl, you form your diazonium. And triple bond. And from there, we have whatever we want to do. Whatever we want to do. So from here, I'm going to give you a series of reactions of what you can do from this starting point. I just mix this with warm water, warm acidic water. You can form a phenol. If I mix this with copper chloride, I can form a aryl chloride. If I copper bromide, the same thing, aryl bromide. Copper cyanide, I can form a aryl cyanyl toluene. So that's a benzonitrile. I'll keep this up. There's a few more I can show. So select all. So some of these are now the bromide and the chloride are rather easy to add. They go the same way. But I can add a fluorine. Fluorine is a little bit harder to add. So fluorine, I have to add from a a borofluoro compound. But if I do that from a aryl diazo, I'm going to form aryl fluoride. If I want to do iodine, remember we kind of did that separately, a different way once when we talked about aromatics. We can have aryl iodide that uses potassium iodide. If I just want to remove the amine altogether, use phosphorus acid. Well, what's it? That's not phosphorus. That's hypophosphorus. But if we do that, this really, really weak acid's going to just kick that off. This is a deamination. We just remove the amine. And in fact, if I add another arene, this is probably one of the most neat. You can form a azodi, where we essentially attack the other side, and we've linked two phenyl groups together. Two phenyl groups together. And of course, so I mean, there's lots of different things you can do with this. As I said, break them down and talk about these a little bit more on Friday. We'll talk about these reactions a little bit more. How we would classify them, what they would be considered under, but so we cross over these. Like how do we form how do we form this? What is this actually named anything? Is there anything special about this? What to note? Okay, that's as far as I'm going to go. Stop it right there. So hopefully you're following along. Hopefully you're looking at some of these. Remember, flashcards, flashcards, flashcards. Some of these are like, oh, you may not know every single condition, like, oh, the one we're going to talk about, one of the first ones we're going to talk about on Friday is the Sandmeyer reaction, which is the copper salt. You may not know that. It's actually like, oh, it has to be copper. But you might be able to recognize, oh, if diazonium is a good leaving group, what is the nucleophile that it's present? Even if you don't know the copper, what you see, oh, nucleophile attack. So we see a nucleophile attacking, and then, oh, you're forming this. You may not know all the conditions, but you should be able to see, well, if this is a good leaving group, we have an SN2 attack going on here. But okay, talk to you more later.